Let's start by defining what is a pressure vessel. A pressure vessel is any container 6 inches and greater that holds a fluid, liquid or gas, greater than 15 psi. A pressure vessel that derives its source of pressure from the direct impingement of the flame or from hot water is not defined as a pressure vessel. Similarly, any vessel designed for human occupancy or that is part of a piping system is not defined as a pressure vessel. Since 1925, the Code of Construction for pressure vessels in the United States has been the ASME, or American Society of Mechanical Engineers, Boiler and Pressure Vessel Code. Section 8, Division 1, is the most conservative and most common code of construction for pressure vessels. Section 2 of the ASME Boiler and Pressure Vessel Code defines the chemical and physical requirements for materials used in pressure vessel construction. What are some of the applications of a pressure vessel? Well, they could be a chemical reactor, a distillation column or tower, a container of pressurized gases and liquids for storage, a heat exchanger, a multi-phase separator, a mixing or blending tank, and there are many more typical applications. Pressure vessels come in all shapes and sizes. Most are cylindrical or bullet-shaped, but they can also be spherical or round, and in some rare cases they can be have cone-shaped elements or other type of geometries. However, a square or rectangular shaped pressure vessel, due to the large internal stresses in the corner elements, are generally not used because they are limited to very low pressures, very close to atmospheric. Pressure vessels should never be supported directly by the piping system. They should have their own separate supports. Horizontal pressure vessels typically use saddles. Vertical pressure vessels that are supported from the bottom will use either a skirt or legs. Vertical pressure vessels may be also suspended from their tops through the use of supporting lugs. Materials used in pressure vessels not only must account for the operating limits, the pressure and the temperatures, but also must be the design engineer must also be cognizant of the effects of corrosion, erosion, or other operating forms of degradation, such as stress corrosion cracking, hydrogen embrittlement, cyclic fatigue, or other failure mechanisms. Nozzles are attachments to the pressure vessel in which piping or other equipment is attached. In the design of nozzles, a portion of the element shell must be removed to put the nozzle in. Whenever you take metal out of the pressure vessel, it weakens the pressure vessel in that area. Therefore, the nozzle that is put back in must account for at least all of the metal taken out. Normally, nozzles 4 inches and below have either sufficient metal to account for the loss of metal, or you can economically use higher wall thicknesses like a Schedule 80 instead of Schedule 40 pipe to replace the metal taken from the shell. In larger nozzles, 6 inches and above, it's not economical to use heavier wall construction. Therefore, the use of repads or reinforcing saddles are typically used. There are several terms related to a pressure vessel design and operating conditions that the engineer must be familiar with. The highest design pressure for any pressure vessel is called its maximum allowable working pressure, or MAWP. It is slightly higher in most cases than the MAOP, which is the maximum allowable operating pressure. On the low pressure side, pressure vessels are designed for either atmospheric pressure, partial, or full vacuum. Pressure vessels subjected to being pumped out, having liquids pumped out, must have design capability so that they will not collapse due to the suction from the pump. Regarding the temperature concerns of material, the most important term is the MDMT, which is the minimum metal design temperature. Certain materials like carbon steel and other materials containing a high content of carbon become less ductile as the temperature drops. When a material loses its ductility, it can crack in service. And therefore, carbon steel materials, for example, are limited to minus 20 degrees Fahrenheit. As materials are exposed to higher and higher temperatures, they rapidly lose their strength and thus limit the amount of pressure that they can adequately and safely retain. When calculating the design requirements for a pressure vessel, most engineers use a commercial grade software like Compress or PV Elite. Each of these programs, as well as many others, use a step-by-step approach wherein they analyze each nozzle, each head, each shell element, each support, and all of internal and external features so that the component that has the weakest pressure retaining capability thus governs the MAWP of the entire pressure vessel. A pressure vessel fabricator must be licensed and authorized by ASME in order to build pressure vessels to the ASME code. In order to obtain a certificate of authorization, a comprehensive review of the fabricator's quality assurance and fabricating process procedures, it must be performed by an ASME audit team. Once a certificate is issued, it is valid for 3 years and must then be renewed at the end of the 3-year period. Nassau EPC maintains an ASME Section 8 fabrication and repair facility in Anahuac, Texas, located just east of Baytown. This concludes our brief talk on pressure vessels today. Thank you very much.